Section 12.2 Vectors. A vector is a quantity that has both magnitude and direction. We denote it using a bold letter or using an arrow. I'll usually draw them using arrows. For a particle that moves along a line segment from point A to point B, the corresponding displacement vector, shown in the figure, has initial point A and terminal point B, and we indicate this by writing an arrow above AB. So because the vector u equals cd has the same length and same direction as v, even though it's in a different position, we see that u and v are equivalent, and we write u equals v. So it doesn't matter where you put a vector. I can put a vector anywhere, and it's an identical vector as long as it has an identical length and an identical direction. It has no position, it has no fixed position, unlike points. The zero vector, denoted by a bold 0, has length 0. If u and v are two vectors positioned so that the initial point of v is at the terminal point of u, then the sum is the vector from the initial point to the terminal point. So let's do an example of that. How about we try drawing the sum of the vectors a and b shown in the figure? Well, because it doesn't matter where I put a and b, I'll just throw a over here somewhere. And that's roughly the same as the a that we're given. And then I need to draw b, but I have to position the vectors so that the initial point of v is at the terminal point of u. So the initial point of b should be at the terminal point of a. So I'll put the b over here, something like that. I mean, I did it a little bit too long, because b is like that, so I don't know, a little shorter. Something like that. So that's b. Well then, the sum a plus b is the vector from the initial point over here to the terminal point over here. So I'll just draw a new vector, and that's the sum. So we call this the triangle law, using the tip-to-tail method of adding vectors. However, another way to add vectors is if I position a over here, but then I position the tail of a and b together, like that. Then I can try drawing a parallelogram. See if I can roughly get it. So the parallelogram is not part of the two vectors. However, using the parallelogram, I can draw the diagonal, and then the diagonal vector will be the sum. And you can see that these two vectors that I drew look the same, and it doesn't matter where they are, so they're the same vector. So we call this the parallelogram law. So we have two different ways that we can add vectors, either tip to tail or using a parallelogram. Next up, scalar multiplication. If c is in a scalar and v is a vector, then the scalar multiple c times v is the vector whose length is the absolute value of c times the length of v, and whose direction is the same if c is positive and opposite if c is negative. And then if c is 0, it just makes it the 0 vector. So this means that if I have a vector and I multiply it by some number, then that makes it longer or shorter. And it changes the direction if the number I multiply is negative. So two non-zero vectors are parallel if they are scalar multiples of each other. So we automatically say that one vector is parallel to another vector if they're just some multiple, because they have no position. They just have length and direction, so that means that I could take one vector and just move it on top of the other one anyway. In that case, the vector minus 1 times v is called the negative of v. It has the same length, but points in the opposite direction. So now we can define the difference between two vectors to mean the sum of a vector and its negative. So let's do another example. How about we try drawing a minus 2b? Alright, let's see if I can do a. Should look roughly something like that. And I'll try drawing b. except that instead of drawing b, I need minus 2b, so I should make it twice as long and then change the direction. So that's the vector I should be drawing. So it should look something like this. Roughly, this is the vector minus 2 times b. And then I want to add them together, and I've put the tail of minus 2b at the tip of a. So now I can just follow along from the tail of a to the tip of minus 2b. And this will be the vector a minus 2 times b. Okay, if we place the initial point of a vector a at the origin of a rectangular coordinate system, then the terminal point of a has coordinates a1, a2, or a1, a2, a3. And these coordinates are called the components of a, and we write a is equal to a1, a2, or in 3 dimensions, a is equal to a1, a2, a3. The representation of a vector from the origin to a point is called the position vector of the point. So there's two things going on here. One is saying that we could take any vector, remember it has no position, and we can just take it and put it so that it starts at the origin. And then we can write down coordinates for that vector, where the first coordinate is just the x value, and the second coordinate is just the y value of the terminal point, because the initial point is just 0. Then we can also say that if we have some sort of point in space floating around, then we can draw a vector, manufacture it ourselves, that touches that point. It ends in that point, and that's called the position vector associated with that point. Okay, next up, given points a, b, the vector representation AB is the difference between the two. So that means that I can take the x-coordinates of the 2 points that I have, and I can subtract them, take the y-coordinates and subtract them, take the z-coordinates and subtract them, and I'll get the vector between those 2 points. What that looks like is I've got 2 points floating around. I want the vector that goes in between them. So the direction that matters, because it would be a different vector if I went up instead of going down. If I want the vector between these 2 points, I just subtract the coordinates for those 2 points. So let's prove this really quick. The vector A equal to O times P, where O is the origin, is the position vector of the point P, which is just going to be something we make up, A1, A2, A3. Let's say that AB is another representation of A, where the initial point is x1, y1, z1, and the terminal point is x2, y2, z2. So then it must be that x1 plus a1 equals x2, y1 plus a2 equals y2, and z1 plus a3 equals z2. And then you can just subtract and see what a1, a2, and a3 would be. What we're basically saying is we've got some point in space, and there's a position vector that goes to it. And then we're saying that there's another representation of the same vector. So let's say floating around over here or something. It's identical to vector OP, except that it has initial point A and terminal point B. And we're saying that if this is true, then it must be that adding this x value over here with this x value over here must give you this x value over here, and so on. Same thing for the y values, same thing for the z values. I only drew my picture in 2 dimensions, but you can imagine it for 3 dimensions. And then you can figure out what the another way of writing the a value, a2 value, and a3 values are for this point, just by subtracting. Okay, how about we find the vector represented by the directed line segment with initial point A and terminal point B, where they're given by this example. So we can label that, how about vector A, and that'll just be what we get when we subtract, like we said. So we start with the terminal point, so we'll take -2 and subtract that 2 from A. So that's our first coordinate. And then we've got 1, -3, well, -3, because I've got to subtract. So I'll take out that -3, and then I've got 1, -4. So -4, 4, 3 is the vector represented by this line segment from these 2 points. The magnitude or length of the vector v is the length of any of its representations and is denoted by the symbol with these bars. We could say, same as the absolute value symbol. We also sometimes denote it like with this, with 2 bars, but we usually will not do that. So if I want the length of the vector a1, a2, then that's just the square root of each of the components squared. And in 3 dimensions, it's the square root of each of those components squared, which you might seem familiar as just the Pythagorean theorem. And that just sort of makes sense. What you can do to prove this is just try drawing a vector. And then you can see however much it goes over here is your a1, and then however much it goes over here is your a2, and then the length of the vector is just by Pythagorean theorem, square root of a1 squared plus a2 squared. So that's not too bad. If a is equal to a1, a2, and b is equal to b1, b2, then the sum is a1 plus b1, a2 plus b2, and the difference is a1 minus b1, a2 minus b2. So the cool thing here is that this is actually consistent with our tip-to-tail method. If you actually draw it out, then you'll see that taking one vector and then placing it on top of the other vector really is the same as just adding whatever coordinates you have for them, the components. And similarly for scalar multiplication, and similarly for 3-dimensional vectors. So how about we try to find the magnitude, sum, difference, and scalar multiples of a couple vectors. So for the magnitude of the a that they gave us, let's do that first. We've got the square root of each of the components squared, so that's 4 squared plus 0 squared plus 3 squared, which is the square root of 25, which is 5. So that's how long a is. Okay, how about a plus b? Well, instead of drawing it, now I can just add each of the components. So that's 4, 0, 3 plus -2, 1, 5, which is equal to 4 plus -2, 0 plus 1, 3 plus 5, which is just 2, 1, 8. Then for a minus b, that's just going to be 4, 0, 3 minus 2, 1, 5. Oh, minus 2, 1, 5. Okay, and that's 4 minus 2, 0 minus 1, and 3 minus 5, which is 6 minus 1 minus 2. Then we want 3 times b, so that's just 3 times -2, 1, 5. And I can move the 3 inside by our theorem, so that's 3 times -2, 3 times 1, and 3 times 5. So we get -6, 3, 15. How about 2a plus 5b? So that'll be 2 times 403 plus 5 times -215, which is just 806 plus -10, 525, and we get -2, 5, and 31. We denote by v2 the set of all two-dimensional vectors, and by v3 the set of all three-dimensional vectors. More generally, we denote by vn the set of n-dimensional vectors. An n-dimensional vector is just an ordered n tuple, so instead of stopping at a3, we could just keep going and adding coordinate after coordinate after coordinate. And then addition and scalar multiplication are the same, even no matter how many components you have. Then, if a, b, and c are vectors in Vn and c and d are scalars, then we have these properties no matter how many components are in our vectors. So a plus b is equal to b plus a. We have commutativity. A plus b plus c equals a plus b plus c. We have associativity. A plus 0 equals a. 0 is our additive identity. And then a plus minus a equals 0. We have an additive inverse of minus a. We also have distribution for scalars. C times a plus b is ca plus cb. We have distribution even when the scalars are inside the parentheses. So those can come out. So we have two different distributive laws. We also have another associative law over scalar multiplication, and we have another identity for multiplication. So next up, we have the vectors I, j, and k. I is just 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. So in 3 dimensions, you could see that if here's the z-axis, here's the y-axis, and here's the x-axis, then here would be vector I with length 1 poking out in the x direction. Here's length j with length 1, here's a vector j with length 1 poking in the y direction, and vector k in the z direction. In 2 dimensions, you just have I and j. So they all have length 1, they point in the directions of the positive axes. And it turns out that any vector in V3 can be expressed in terms of I, j, and k. I actually call them standard basis vectors, but it's okay. Any vector in V2 can also be expressed in terms of I and j. And proving this is pretty easy. We just write a vector as a1, a2, a3. And that means that we can decompose that into a 1, 0, 0 plus 0, a 2, 0 plus 0, 0, a 3, just using vector addition, which means that we can undo scalar multiplication by pulling out each of those scalars. And then there we go. That's a1 times I plus a2 times j plus a3 times k. So it just gives us an alternative notation. So as an example, let's express the vector 2a plus 3 in terms of I, j, and k. So we've got 2a plus 3b equal to 2 times the vector for a in terms of I, j, and k, so that's I plus 2j minus 3k. Just another way of saying the vector 1, 2 minus 3. And then we'll add that to 3 times the vector for I plus 7k. Notice in this case it would be the vector 4, 0, 7 because j is 0. So we get 2i plus 4j minus 6k when we distribute our 2, and we get 12i plus 21k after distributing our 3. So combining our i's and k's, we get 14i plus 4j plus 15k. So it's the vector 14, 4, 15. A unit vector is a vector whose length is 1. For instance, I, j, and k are all unit vectors. So in general, if we have a non-zero vector, then we can turn it into a unit vector we'll call u by dividing it by its length, or multiplying it by 1 over its length. So let's prove this really quick. How about we let some constant equal 1 divided by the vector's length. So then the unit vector is the constant times a, and c is a positive scalar. So it must have the same direction as a, because scaling a vector doesn't change its direction. So let's show that the unit vector has length 1. Well, we've got the length of u equal to the length of c times a, because that's what we said u is equal to. So we can say that the length of c times a is just the absolute value of c times the length of a. And then the absolute value of c is just 1 over the length of a, as we said what c was. And times a, that just cancels and gives you 1. So let's do an example, finding the unit vector in the direction 2i minus j minus 2k. So we will take the length of 2i minus j minus 2k, and the length, as we recall, is equal to the square root of each of the components squared, added together. It's just our Pythagorean theorem, basically. And that's going to be the square root of 9, which is 3. So that means we just have to multiply by 1/3. We just divide by 3, and we'll have the unit vector version of our vector 2i minus j minus 2k. So that means that our unit vector is 2/3 times I minus 1/3 times j minus 2/3 times k. And you could try taking the length of this vector and you'll see that it actually is 1. Last but not least, a force is represented by a vector because it has both a magnitude, measured in pounds or newtons, and a direction. If several forces are acting on an object, the resultant force experienced by the object is the vector sum of these forces. So as an example, we've got a 100-pound weight hanging from 2 wires as shown in the figure. Let's find the tensions, which are the forces T1 and T2 in both wires, and the magnitudes of the tensions. So in order to try to do this, how about we draw a vector for the weight? So we can call that vector, maybe I should not poke the arrow out so much. Okay, we'll call that vector W. Notice that it's going down 100, so we could say W is minus 100. How about we now try to figure out what these guys are using that fact? Well, if I were to draw these vectors as a sum, it would be the sum of these 2 vectors. So because this angle is up over here, it's an alternate interior angle to this angle over here, so this must be 32 also. Similarly, I could draw up over here and see that this angle over here must be 50. So this means that I could write T1 equal to however far I go over here times I, and however far I go up here times j. So I just need to know how long this thing is. So let's see. If this over here is the hypotenuse of this triangle, then the hypotenuse is the length of t1, just the length of the vector. So that means that if I want to know how long this is over here, I could say that this is the adjacent side, so the cosine of 50 is equal to this side divided by t1, and then solving for that adjacent side, I just get that it must be equal to t1 times the cosine of 50. However, it's going in this negative direction, so I'll throw in a negative. So we could say that for the I component, it's going to be minus the length of t1 times the cosine of 50. Now let's see how much it's going up. Well, how much it's going up, we can use sine. The sine of 50 is equal to this opposite thing divided by the hypotenuse. And it's positive. So that means that it's going up by the length of t1, the hypotenuse, times the sine of 50. So that's our jth component. Unfortunately, we have no k because we're just in 2 dimensions. So now let's worry about the other one, t2. We can do basically the exact same thing to see that t2 will be the length of t2 times the cosine of 32 degrees, which is positive because we're going this way now, and the direction going up is also positive. It's going to be the length of t2 times the sine of 32. Okay, so then we know that our vector w for our weight is minus 100 times j, so that implies that if I take t1 and I add it to t2, then that should equal minus w, which would be 100 j. Notice I'm using j because it's going straight down. J is our up or down because it's for y. Okay, so let's use this to come up with some sum to equal 100j. So I'll replace t1 with what I calculated for t1, and I'll replace t2 for what I calculated for t2 in this formula over here. So we have minus t1 times the cosine of 50 plus the length of t2 times the cosine of 32, because I'm grouping together the I components. And then I'll group together the j components, so that's the sines. So sine of 50 times t1 plus sine of 32 times the length of t2. So altogether, this must equal 100j by this equation over here. Okay, so that means that I have all of these i's just equal to 0 because there is no 0 on this side. So this must equal 100 and this must equal 0. It's 0i plus 100j. So I can write minus the length of t1 times the cosine of 50 plus the length of t2 times the cosine of 32 equal to 0 for my i's. And I can write that the length of t1 times the sine of 50 plus the length of t2 times the sine of 32 is equal to 100. So why don't I solve for t2 in terms of t1 in this equation, and then I can plug it into this one. So I get t1 times the sine of 50 plus the length of t1 times the cosine of 50 over cosine 32 times the sine of 32, because this is what you get when you get t2 by itself in this equation, and then we would just replace that over here, and we keep our sine 32. So that equals 100. I just plugged into my second equation. So what I can do is factor out t1, so I get that factor the length of t1, so I get the length of t1 times the sine of 50 plus the cosine of 50 times sine of 32 over cosine of 32 must equal 100. Okay, so now I know what t1 is. I can just, with the length of t1, I can just take 100 and divide it by this whole mess. Okay, so that means that the length of t1 is 100 divided by the sine of 50 plus, well, I can write this as tangent, so tangent 32 times the cosine of 50. And if we use a calculator, we see that's about 85.64, and I'll write LB for pounds. And then for t2, that length, now that we know what t1 is, we could just plug that into our formula for t2, which is t1 times cosine of 50 over cosine of 32. It's what you get by solving that first equation for t2. And that's just going to be 64.91 pounds. Okay, so now we go back to where we said t1 is equal to this mess times its lengths. We now know what the length is. We could just plug in and multiply by cosine 50 and sine 50, and we'll get what the vector t1 is. And similarly, we can plug in for t2, and we'll see what those guys are. So doing that, we plug in, and we get that vector t1 is approximately minus 55.05i plus 65.60j, and then vector t2 is about 55.05i plus 34.40j.